Hello and welcome to the Terran Space Academy, where we help prepare you for a future in the space industry. Don't forget to stay connected, let us know what you like, and help support us on Patreon, so we can keep bringing you great lessons in space science. Even Musk haters who want to belittle anything he touches would have to admit that SpaceX has had an amazingly successful last few years. The Falcon 9 booster reuse is so common that one not being recovered intact is now news. SpaceX sent more mass to orbit last year than any other launch provider, and has another 144 flights planned for 2024. But I want to draw your attention to the launch of a Cygnus resupply capsule to the ISS.
Thanks. We're at T-minus 7 minutes 30 seconds and counting to the launch of the Falcon 9 rocket and the Northrop Grumman Cygnus cargo craft, which, as we said, is delivering about 4 tons of science and supplies to the space station. You know, science for every crew that lives and works on board the station is the main objective of activities up on orbit.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, ignition, engines full power, and liftoff. Go Cygnus, go Falcon.
Falcon 9 and Cygnus begin their flight, taking aim on the International Space Station. Pitch and roll program are in. Falcon 9 arcing out to the northeast.
At T plus 40 seconds, Falcon 9 has successfully lifted off from Space Launch Complex
Power and
40.
telemetry nominal.
This is our 10th mission of the year and second to the International Space Station. And we've throttled down our engines in preparation for max Q, which is coming up here in a few seconds. This is the largest structural
Vehicle
load.
supersonic.
This is the largest structural load that the vehicle will see on ascent.
Max Q.
And great news, we've passed through max Q and are throttling those engines back up. Again, those 5 events coming up in a few seconds. MECO, stage separation, SES-1, the boost backburn starting up, as well as fairing separation.
MECO. Stage separation confirmed. And back ignition. Stage 1 boost back startup.
And there we've had MECO, stage separation, the MVAC engine on the second stage ignited, as well as the boost backburn starting up on the first stage vehicle. And some awesome views there on your screen. On your left-hand side is a view from the first stage. On your right-hand side, a view from the second stage.
Fairing separation confirmed.
And excellent news, we were able to see and hear the call out for confirmation of fairing separation. You can actually see one of the fairing halves falling back to Earth on your right-hand screen.
Stage 1 boost back shutdown.
And we heard that call out, and you can see on your left-hand screen that the engines on the first stage vehicle have shut down, and that concludes the boost back burn for the first stage vehicle. You can also see that the grid fins are now deploying on the first stage.
Both vehicles are following nominal trajectory.
And great call outs that both vehicles are on nominal trajectories.
Stage 1 entry burn startup.
We just heard that call out, and you can see on your left-hand screen that the engines on the first stage vehicle have reignited. It's just about a 17-second burn.
Stage 1 entry burn shutdown.
And
Stage
awesome,
1 FTS has safed.
awesome tracking view of our first stage vehicle. As you can see that the entry burn has concluded. And the first stage vehicle continues to make its way back down to Earth.
Both vehicles continuing on a nominal trajectory.
And this is an incredible view that we are getting of the first stage vehicle heading back to land. Right now it's using its 4 grid fins to guide
Stage 1 transonic.
to guide the vehicle during its descent. And this is amazing. You can see those 4 grid fins deployed. What a view that we
Stage 1
have.
landing burn.
And you can see that the landing burn has begun for the vehicle. Let's watch as Falcon 9 touches back down on land.
Stage 2 FTS has safed.
Stage 1 landing leg deploy. Stage 1 landing confirmed.
What a sight to see. Falcon has touched down. This booster just completed its 10th flight and the 268th successful landing of an orbital class rocket, including both Falcon 9 and Falcon Heavy boosters. That was such an incredible view to watch. That view that you see there on your screen is looking forward at the payload. And separation coming up here in a few
Cygnus
seconds.
deploy confirmed.
And an incredible view. You can see the Cygnus spacecraft drifting away from Falcon 9's second stage, confirming successful spacecraft separation.
Today's delivery is designed to improve robotic surgeries on Earth, 3D printing techniques, and the growth of cartilage and microgravity. So let's take a quick look at the science aboard Cygnus.
Cygnus is built by the American company Northrop Grumman. It has a launch mass of 6,600 kilograms and a dry mass of 3,400 kilograms, leaving a little more than 3,000 kilograms for payload. It has a volume of 198.9 cubic meters and uses its solar panels to produce up to 3.5 kilowatts of electrical power. The Cygnus was first launched in 2013 aboard an Antares rocket. 20 of these have been launched since. 18 of these were aboard the Antares, which you will remember used Russian RD-180 engines and had to be retired for national security reasons. Northrop is working on an updated Antares called the 330 that will use Miranda RP-1 and liquid oxygen burning engines made by Firefly Aerospace with the help of Ukraine. But these won't be available until mid-2025 at best. The rest of the Cygnus missions had all been launched on the Atlas V. Built by the United Launch Alliance, the Atlas V was retired in October of 2023. But on the 30th of January, a Cygnus launched on a SpaceX Falcon 9 rocket. Why would SpaceX agree to launch a competitor's spaceship? I think it's because there is no better way to advertise the dependability of your rockets than when your competition has to come to you to fulfill their launch contracts, because their rockets are too far behind schedule. SpaceX has a history of helping out its competition in other ways also. It launched the OneWeb satellites, which compete with Starlink, when the Russians pulled their rockets from the European Union's Guiana Space Center. Jeff Bezos is being sued right now for insisting that his Kuiper satellites wait to be launched on New Glenn rockets. Remember that Amazon is a publicly traded company, and Bezos has an obligation to do what is in the company's best interest. And Amazon is not Blue Origin. They are separate entities. SpaceX has kept everything, Falcon, Starlink, and Starship, under one house. This makes things a little simpler in some ways. The Cygnus that was just launched is one of 4 ISS resupply capsules available today. These are the Cygnus, Soyuz, the JAXA HTV, and Dragon, since the European Space Agency retired its automated transfer vehicle. Of these, only the Dragon capsule can return cargo to Earth, though the Sierra Space Dream Chaser should soon be in operation and will be able to do this also. At a length of 5.1 meters and a diameter of 3.07 meters, the Cygnus fits easily in the SpaceX fairing, which is lucky, I think, because fairing size is one of the few weaknesses of the Falcon 9 design. The Falcon 9 rocket is 3.7 meters wide, because this is about the limit of what you can drive down an American highway. That limits the fairing size. Here you can see a graphic showing the relative sizes of the Vulcan and Falcon fairings. The Falcon fairing is smaller, limiting what this powerful rocket can carry to orbit. But this is about to change. Here we see a SpaceX fairing with a length of 22.5 meters and a diameter of 5.2 meters, compared to all these other rocket systems. It is important to note here that the SLS was planned to eventually have a larger payload bay than the Starship, and eventually lift as much as the Saturn V, though not as much as the new estimates of Starship's ability with the Raptor 3 engines. Let's look at what is planned for Starship. We've covered how the Raptor 3 is a lot more powerful than the Raptor 2. This allows you to leave the ground with more mass, and as every rocket scientist will tell you, mass to orbit is determined by only two things: the efficiency of your rocket engines and the mass. Rockets use stages because the dry mass of the structure needed to get off the ground is of no use once the propellant in that stage is expended. Single stage to orbit is possible. The Starship booster could in fact work for this purpose, getting about 17 metric tons to low Earth orbit. But it would almost certainly not survive re-entry, much less have enough propellant to come back and land if it could. So the current Starship system is two-stage, and with more powerful engines, SpaceX can make this entire system bigger. Elon Musk has spoken of adding another 30 meters to this rocket, bringing it from 120 meters to 150 meters. They'll need to extend the height of their tower, of course, and adjust the quick disconnects. That would mean stretching one or both of these stages. Let's look at the options. 30 meters is almost exactly 100 feet, making the Starship start to look as stretched out as a Falcon 9. I don't think the payload bay is going to get a whole lot larger, so let's look at this going into the propellant tanks. First, for overall mass, a cylinder that is 30 meters tall with a diameter of 9 meters will have a volume of length times pi times the radius squared gives us 1,908.5 cubic meters. The propellants used by Starship are liquid methane and liquid oxygen. SpaceX does not give us the oxidizer to fuel ratio for the Raptor engines. Stoichiometrically, the ratio would be 4:1, and Wikipedia says it's around 3.8:1. Since we want to burn fuel rich, that seems reasonable. That would mean that for every 1 kilogram of methane fuel, you will need 3.8 kilograms of oxygen. Every cubic meter of liquid methane has a mass of about 490 kilograms, so its density is 490 kilograms per cubic meter. Every cubic meter of liquid oxygen has a mass of about 1,250 kilograms. If we cross-multiply these, we can cancel out the kilograms and get our relative volumes, and we see that we need about 40% of the tank volume to be liquid oxygen, while the other 60% would be liquid methane. If we multiply the density of these propellants by the percentages and available volume, we can get an extra 958 metric tons of liquid oxygen and 560 metric tons of liquid methane. The launch mass of Starship right now, with a 100 metric ton payload, is supposed to be 5,000 metric tons. If we add 1,518 metric tons to this, we get 6,518 metric tons total. Each Raptor 3 rocket engine is supposed to have a maximum thrust of 230 metric tons. 33 of these would give us 7,590 metric tons of force. The current Starship has a mass of 5,000, and it has a thrust-to-weight ratio of 1.52. If we add all this extra mass, we are down to just 1.16 at launch. This seems too low. Let's change things a little. From what I can find, each Starship ring is 72 inches or about 1.8 meters tall. That seems to be the limit of sheet steel width in the United States. 30 divided by 1.8 equals 16.7. We'll add 9 rings to the booster, and 6 to the Starship propellant tanks, with the last 1.7 going to the payload bay. That would divide our 30 meters into 16.2 for the booster. That would add 820 metric tons of propellant there, 10.8 meters for the Starship tanks, adding another 546 metric tons there, and 3.06 meters, or about 10 feet, going to the payload bay. That reduces our total added mass by 152 metric tons, as the payload bay volume doesn't hold propellant. Let's see where that puts us. These rings would increase our dry mass also, which we haven't factored in. In the early days, each ring had a mass of about 1,600 kilograms. They should be a little lighter now as the steel is not quite as thick. Let's say 1,500 kilograms, so 1.5 metric tons per ring. Adding 9 of these to the booster would add 13.5 metric tons to the booster dry mass. This brings us to 193.5, so let's say 195 metric tons of booster dry mass. The Starship has a dry mass of 120 metric tons, and adding 6 rings would bring it to 129, with the stretched payload bay adding another 2.55. We'll go with a total of 132. Let's look at thrust-to-weight ratios now. With our added rings and propellant mass, we get a total mass of 6,393 metric tons. Dividing that into 7,590 gives us a ratio of 1.19. That's a little better. Now let's keep 5% of our propellant to come back and land. That has us burning just a little more than 4,000 tons in the booster, and 1,650 in the Starship. We lift off with a launch mass of 6,393 metric tons and burn 4,009 metric tons of propellant, at a specific impulse of 330 seconds. Converting that into exhaust velocity by multiplying by 1g, we get 3,237 meters per second. Putting the exhaust velocity, initial mass, and final mass into our rocket equation gives us a delta V of 3,193 meters per second. Now we separate the booster and its reserve propellant mass, which totals 406 metric tons, and hot stage the Starship with a mass of 1,978 metric tons. We burn 1,659 metric tons with a specific impulse of 380 seconds, giving us an exhaust velocity of 3,728 meters per second. We will end up with a final mass of 319 metric tons and a delta V of 6,799 meters per second. That gives us a final delta V of almost 10,000 meters per second. We only need 9,400 to get to low Earth orbit. So we could take it to a higher orbit, or we could bump the payload mass up to 160 metric tons with no problem. Our stretched Starship, with a payload bay of almost 1,200 cubic meters, would have more volume than the entire ISS, or 3 of the Sierra space life habitats. What should SpaceX do with all this space in orbit? Starship has already been selected to place the Airbus Starlab into orbit. This is a different habitat from the one designed by NanoRacks and Lockheed Martin that I mentioned and kind of made fun of in this lesson. The European one is a joint effort between Airbus and Voyager Space. Voyager Space is a space habitat company founded in 2019 in the United States. Starlab is the European version of the Sierra space life habitat, just larger. Each one has about half the volume of the ISS, with a diameter of 8 meters, which is 26 feet. That turns out to be perfect for the Starship payload bay, which has a diameter of 9 meters. According to Airbus, they were looking at multiple launches to get their Starlab into orbit, which would have been quite expensive. But the current Starship design can do this all in one launch, and the Starlab will be ready to use as soon as it's placed in orbit instead of having to be assembled in pieces. What else can SpaceX do? SpaceX should allow companies to build inflatable habitats that can be completely contained in the Starship at launch and inflated in space. It makes no sense to use steel walls and floors in freefall. These habitats should be made of plastics and other synthetic fibers, as these would provide excellent radiation protection. Once a Starship was in orbit and the habitat inflated, a Dragon capsule could be sent up with 7 crew members. It cost over $100 billion to build and assemble the ISS. One Starship would be able to provide much better facilities to the world's scientists. Just like the recent AX-3 mission allowed the nations of Turkey and Sweden to send their first astronauts into space, nations could lease Starships, contract Falcon 9 flights, and start creating a true orbital habitat system. Industries could put zero-G factories into orbit, for bioprinting organs and making perfect crystals. This would truly revolutionize the space industry. What else could the Super Starship do? If we strip it down to non-reusable, we can send a lunar lander with a stretched Centaur hydrogen-fueled propulsion module on its way to a lunar orbit. We could then use an SLS to send an Orion capsule to dock with it at the moon's orbit, transferring astronauts for a lunar landing. After exploring the lunar surface, they can ascend back up to dock with Orion and head back to Earth. The main holdup to this plan is a functional lunar lander. Perhaps here also, SpaceX could reach out to Blue Origin. Or if that proves impossible, equip the nose cone of Starship with liquid hydrogen and oxygen propellant tanks. The super efficient RL-10 rocket engines used on the Centaur second stage would be a very good choice. These can be throttled down to 15% full thrust, allowing a controlled landing and liftoff. We would still need the Orion to come home, as nothing else exists that can survive a return from lunar orbit. The great thing is that we have options, and that's a big change from just a couple decades ago. Something to think about. Hello, fellow space scholars. I wanted to thank you for being here. This channel started 4 years ago for many reasons. One of them is that I love to teach and have always wanted to learn how to create video lessons. Another was my frustration at the lack of facts in space news. I wanted to make sure that those truly interested in space science had somewhere to go to learn about the equations that make rockets possible, to give you the tools to make your own evaluations of different launch systems. But as important as understanding the equations are, they limit my channel to those with a serious interest in understanding space science. As many of you know, the YouTube algorithm promotes broad topics that are easy to understand. Our space science lessons, however, require a more detailed understanding, and I don't want to dumb the lessons down. But that makes the target audience a lot smaller. To take this channel to the next level will require that I invest more time and resources, and that will require your help. Therefore, I really need your support via Patreon or YouTube membership. Just a little bit every month can make a huge difference, and would be greatly appreciated. I thank you so much, dear friends of rocket technology, for your continued support, and I can't tell you how much it means to me. Thank you, and stay safe. At Astra Pro Terra.